Hello and welcome to StockSapiens. I'm going to introduce the research paper Jungsang Kim and Chris Monroe created in 2013. If you are IonQ investor, you should know about this thesis. This research paper, named Scaling the Ion Trap Quantum Processor, is the paper that IonQ could be incorporated thinking that scaling quantum computing is possible. I think it's time to go to the basic and let's think about how and why IonQ could be started. We'll delve into a pioneering thesis by Chris and Jungsang, the innovative minds behind IonQ Incorporated, and how the research on ion trap quantum processors is paving the way for a new era in computing. Understanding quantum computing. Let's start with the basics. Quantum computing is a radical departure from traditional computing. In classical computing, we deal with bits, which are like tiny switches that can either be off or on, meaning 1 or 0. But quantum computing introduces us to the quantum bit, or qubit. Qubits are like magical switches that can be both off and on simultaneously, thanks to a quantum property called superposition. This ability allows quantum computers to process vast amounts of data at incredible speeds, far outpacing even the most powerful supercomputers of today. The magic of qubits. Qubits are at the heart of quantum computing, and their behavior is what makes quantum computers so uniquely powerful. In classical computing, doubling the number of bits doubles the processing power. But in quantum computing, thanks to superposition and another property called entanglement, the increase is exponential. Imagine if every new member added to a team could double the team's productivity. That's the kind of leap we're talking about with qubits. Challenges in quantum computing. However, harnessing the power of qubits is incredibly challenging. Quantum states are delicate. They can be easily disturbed by the smallest environmental changes, a problem known as quantum decoherence. Moreover, scaling up the number of qubits, which is essential for building practical quantum computers, presents significant technical hurdles. Ion trap quantum processors. This is where the groundbreaking work of Monroe and Kim comes into play. They focused on ion trap quantum processors, where individual ions, charged atoms, are trapped and manipulated to act as qubits. These ions are held in place by electric fields in a vacuum, isolated from external disturbances, which makes them ideal for maintaining quantum states. How ion traps work. In ion traps, lasers and microwaves are used to control the quantum state of the ions. The precision and control required here are astonishing. It's like performing a symphony where each musician is a single atom, playing in perfect harmony with the rest. Scaling quantum processors. Monroe and Kim's thesis primarily addresses the challenge of scaling these systems. They proposed an architecture for a scalable quantum processor using ion traps. The key idea is to arrange the ions in a linear chain and use laser pulses to perform quantum operations. By carefully controlling these operations, they demonstrated that it's possible to scale up the number of qubits without losing control over the system. Quantum CCD. One of the most innovative concepts from their work is the quantum charge-coupled device, or quantum CCD. It's a method for moving ions around within the trap, allowing for more complex and larger-scale quantum operations. This approach is akin to having a dynamic quantum circuit, where the pathways of interaction between qubits can be reconfigured on the fly. Applications of quantum computing. The implications of scalable ion trap quantum processors are vast. Beyond just faster computing, they open doors to solving complex problems that are currently intractable for classical computers. This includes everything from drug discovery and material science to solving complex optimization problems in finance and logistics. The future of quantum computing. As we speak, companies like IonQ are building on these foundational ideas to create practical quantum computers. The journey from theory to reality is filled with challenges, but the progress made so far is promising. We're on the cusp of a quantum revolution, where the computational power at our disposal could dramatically change the world as we know it. Quantum entanglement, a closer look. Another fascinating aspect of quantum computing is entanglement. When qubits become entangled, the state of one qubit instantly influences the state of another, regardless of the distance between them. This bizarre and counterintuitive phenomenon is not just a scientific curiosity. It's a powerful resource for quantum computing, enabling complex calculations that are beyond the reach of classical systems. The quantum leap. Quantum computing represents a quantum leap in our technological capabilities. It's not just about speed. It's about a new way of processing and understanding information. Monroe and Kim's thesis is not just a blueprint for a new type of computer. It's a roadmap for a new era of technology. Before we conclude, let's delve into a critical aspect of Monroe and Kim's thesis. The scalability of ion trap quantum computing. This is the crux of their work and the key to unlocking the vast potential of quantum computing. How did they envision scaling these systems to handle more complex tasks and computations? Monroe and Kim identified the primary challenge in quantum computing as scaling up the number of qubits. To address this, they proposed a multiplexed architecture called the quantum charge-coupled device, QCCD. This approach involves the entanglement of small numbers of ions through their collective motion in a single chain and the classical shuttling of individual ions between different trapping zones to propagate the entanglement. This architecture requires precise control of the ion positions during shuttling and may require additional atomic ion species to act as refrigerator ions to quench the excess motion from shuttling operations. Their thesis outlines how the QCCD approach could be used to entangle larger numbers of qubits effectively. For example, it involves the sequential entanglement of small numbers of ions in a single chain, then moving individual ions between different trapping zones. This way, they could scale the system beyond 10 to 100 trapped ion qubits. They also discussed the challenges of scaling to thousands or more qubits in the QCCD due to the complexity of interconnects, diffraction of optical beams, and the extensive hardware required for qubit control. Moreover, Monroe and Kim's vision included the use of photonic gates and joining remote crystals to scale beyond the QCCD in a modular architecture. By linking separate registers of trapped ion chains with photonic interfaces, they proposed a system where an entangled qubit pair could be generated between two registers and then used to implement a 2-qubit gate between ions belonging to each register. This approach isn't limited to trapped ions and can be generalized to other physical systems with strong optical transitions. In their thesis, they acknowledged the daunting requirements for large-scale quantum computer hardware given the exponential sensitivity of large superpositions to errors and leaks to the environment. However, they also pointed out the existence of error correction codes that allow for the generation and stabilization of complex quantum superposition states, giving hope that useful, fault-tolerant quantum computers will eventually be realized. Conclusion. In summary, Monroe and Kim's thesis on scaling the ion trap quantum processor laid out a visionary roadmap for advancing quantum computing. They not only tackled the theoretical aspects but also provided practical solutions and architectures for scaling quantum systems. Their work is foundational for IonQ Inc. and pivotal for the future of quantum computing. As we explore this exciting field on StockSapiens, let's remember that we are witnessing the unfolding of a technological revolution, one that promises to redefine computing and solve some of the most complex problems facing humanity. Thank you for joining me on this enlightening journey into the heart of quantum computing. If you're intrigued by the future of technology and want to stay updated on breakthroughs like these, don't forget to like, share, and subscribe to StockSapiens. Until next time, keep exploring the quantum frontiers.